my dear VLSI aspirants. Welcome to Deep Silicon VLSI YouTube channel. Guys, this is Unit 2 Boolean Algebra and K-Map. The first question. Without any delay, let's dive into the question number 1. The number of distinct Boolean expressions of 4 variables is 16, 256, 1024, 65, 536. Guys, let's consider only one variable, that is A. Okay? If it is the variable A, how many possibilities will be there? It could be either 0 or 1. So, I can say that if the variable is A, it could be 0 or 1. Similarly, if it is A, B, two variables 0, 0, 0, 1, 1, 0, 1, 1. Okay? Now, let's see the functions. Let's see the first function f1. That function is simply 0. Means for input is A is 0, output is 0. A is 1, output is 0 only. Or else there is another possibility, f2. It's 1 only. Irrespective of the input A 0 or 1, output is always 1. That's also one of the function. And another one, f3. That could be, guys, maybe when A is 0, your output is 0. When A is 1, your output is 1. This could be possible. Or else f4. If input is 0, output is 1. If input is 1, output is 0. So these are the possible functions for a single variable. This one. Now guys, if it is one variable A, how many rows I can expect? 2 rows. Similarly, if it is 2 variable, I can expect 4 rows. 0, 0, 0, 1, 1, 0, 1, 1. Now, I am going to write number of rows is equals to 2 power number of variables. Got it, guys? In this case, only one variables we have taken. Therefore, the number of rows are 2. Similarly, how many functions are there, guys? It depends upon 2 power number of rows. Hence, I can say number of distinct Boolean functions is equals to 2 power number of rows. In our example, the number of rows are 2 and we got the functions 4. 2 power number of rows. Now, if you want to interconnect the number of Boolean functions with respect to variables, then we can say the number of distinct Boolean functions is equals to 2 power number of variables. It is like 2 power number of variables. Let's assume n. N is a variable. Then the answer is like the expression 2 power n. Now, how much they have given the variables? 4 variables. Then it is 2 power 4. What is 2 power 4, guys? 16. 2 power 16. 2 power 16 can be written as 2 power 6 into 2 power 10. 2 power 10 is 1024. 2 power 6 is 64. So 64 into 1024, it could be 65, 536. Okay, guys, even in our digital, here 1024 refers K. Sometimes in the options, instead of 65, 536, they might give 64K also. Both are same. Here K refers 1024 2 power 10. Hence guys, For this particular question, the right answer is option D, 65,536 or 64K. Got it, guys? See here what we want to highlight. Some of the people already before visiting this video, you know 2 power 2 power n. But you should know how it has come, how it has been generated, right? So this is what here the number of distinct Boolean functions for an n variables. Boolean algebra simplification in the best possible way. Okay? Question number 2. The Boolean function x plus y into x bar plus z into y plus z is equal to which one of the following expression? There are 4 expressions. We know very well. A Boolean function can be represented in SOP or POS, sum of product form or product of sum form. Hope you know this equation is in product of sum form, POS form. Okay. Now we want to simplify the expression. Immediately what we accidentally we get it is, we'll take the multiplication and we will simplify. If I take that approach, let's take that approach, method 1, where I multiply directly, so that x into x bar 0, x into z xz, x bar y yz, again into y plus z. Again if you multiply xyz xz, x bar y, x bar yz, yz, yz. Now guys, here yz is common. Yz into x bar plus 1, you get y bar z only. Anyway, this x bar y is as it is. However, these two terms, xz you can take it common, xz into y plus 1, so that it's 1, hence it is xz. This is the expression. Now what we can do is, here we can add x into x bar, because x into x bar is 0 only, plus xz, x bar y, y bar z. Therefore now if you take common x, x bar plus z plus y, this is y, right? So this is y, if you take common x bar plus z. Now guys, here you can rewrite it as x plus y into x bar plus z. This is the final expression, but guys, it requires lots of efforts to simplify, and suddenly you should get the thought here x bar z is there, so that we can take x into x bar, that many more number of assumptions. Instead of that, why are you waiting? Why don't you go for K-map? Whenever the variables are 3, above 3, it's best to consider K-map simplification only. Now, it is a 3 variable function. Let's consider here using K-map. It is like this, where a 3 variable K-map can be expressed as, let's consider this is x, y, z. This is x bar in POS format, because the given expression is POS. Now it is y plus z, y plus z bar, y bar plus z bar, y bar plus z. Now guys, x plus y, here this x is there, y is there, it could be z or z bar, hence you can take this for this. Similarly, x bar plus z, x bar, it could be z, it could be y or y bar, hence this. And now the last one, y plus z. y plus z is always like already there. Now like we filled the K-map. Now let's simplify. If you take this simplification so that we get x plus y, isn't it? Yes. Similarly, if you map here the pair, then it can be x bar, y bar gets cancelled, x bar plus z. Now guys, the simplified expression is x plus y into x bar plus z. We got this. When compared with this, method 2 is very clear and easily accessible, isn't it? Yes. However, guys, apart from method 1, method 2, there is a method 3 also. What is that method? In Boolean algebra, we have different laws like involution law or else De Morgan's theorem, etc. In the same way, we have consensus theorem. Got it? As per this consensus theorem, if there is a function, it is a 3 variable. However, only 2 variables are there in each product term, each max term or sum term. This is x plus y, z is missing, y is missing, x is missing. So in every sum term or max term, 1 variable is missing. If it is the case, then the output expression will be the one which has complement and in the true form. That's it. So that from here, what we can say is here we have complement x bar. You take this term and in true form x plus y. So that it is, answer is like for this, as per the consensus theorem, the answer is like x plus y into x bar plus z. Yes, you can tell in this way also. This is method 3. Okay guys, you can cross check as per the given equation. And remember one important point, it is not like only for POS. It will be applicable to sum of product form SOP also. For example, let us consider here in a SOP format, xy plus x bar z plus yz is equals to xy plus x bar z also the same. See, please don't think consensus theorem is applicable only for POS form. It is applicable to SOP form also. Got it guys? This is what the consensus theorem like importance. You can easily tell the answer, whichever is the having the true complement form and the true form. You take those terms. That's it. That will be your answer. This is what the simplification guys. And the takeaway from this video is, if the number of variables are more than 3 or equal to 3, it's better to use K-map unless otherwise it is mentioned. Moreover, you need to remember the consensus theorem also. It is not like De Morgan's law, involution law, idempotent law. No, you need to remember the consensus theorem also. And consensus theorem is applicable to POS and SOP also. Okay guys, conversion of the simplified expression into the standard canonical expression. It could be either SOP or POS. Let's dive into the question number 3. How many minterms excluding redundant terms does the minimal switching function f of v w x y z is equals to x plus y bar z originally have? 16, 20, 24, 32. This question indirectly telling us how to convert this minimized expression into canonical expression or standard SOP expression, because it is in the SOP form, isn't it? Yes. Now guys, usually if it is semester exams, if there is a time permits and they are giving 5 marks or 6 marks, etc., then what we can do is, here instead of this x, you can write it as here, as per this series, we can write v plus v bar into w plus w bar into, anyway x is there, into y plus y bar into z plus z bar. You can write in this way. Here x is there, the remaining options of those terms you are assuming it as a v plus v bar, because v plus v bar is 1 only, nothing has changed. Similarly, even for this second min term also, you can rewrite it as v plus v bar, w plus w bar, x plus x bar into y bar z. This one, guys. Now if I take again v into w bar, it will be a lengthy solution. But instead of that, there will be a very like a simple shortcut method to solve this question in a fraction of seconds. Yes, let me draw this. It is a 5 variable Boolean function. No, then what is a K-map? Here obviously we can take in this way, one for v bar, another one for v. Let's assume this is for v bar, and again here v. It's a 4 variable K-map, and individually it is like a 4 variable, and this is v bar and this is v, and then the remaining it is like wx yz. Right, guys? Here it is the same, like w bar x bar, w bar x, wx, wx bar. Similarly here y bar z bar, y bar z, yz, yz bar. The same applicable to here also, because everything is same except v. This is v bar and that is v. Okay, now let's consider the solution using K-map. Guys, here what they told x now, wherever x is there, you can consider all those min terms. Right, now here you see x is here, here x is there, then you can consider all of these terms. Even v bar also included, we need x, that's it. Hence you can take all of these, right? This is over, and then y bar plus z, y bar z, wherever y bar z is there, you can take them as it is. Here y bar z is there, here also y bar z is there, because this is also y bar z only, na? Hence here y bar z, you take all of them. Yes, taken. And he told excluding redundant terms. Then how many like min terms are there for this particular function x plus y bar z? Then guys, here 8, 8, 16, 17, 18, 19, 20. Hence guys, for this particular function, simplified function x plus y bar z, the total number of min terms present in this expression is none other than option B, 20. And here one important point that we must consider and we must know, and people might be in ambiguity. So this is only the simplified expression, right? Here you require less number of hardware elements. Obviously one NOT gate, one AND gate, one OR gate, that's enough now. If you convert into again standard SOP, then you require more number of hardware elements, isn't it? Yes, then why are you converting? Yes, I agree. As per the procedures, yes, we need to know how to convert a minimal function into a standard SOP. Agree. But where do you need? In standard SOP, you require more number of hardware elements, right? You can ask me. Yes. But the answer is, guys, if you have the criteria saying that you need to implement using multiplexer only, you need to implement using demultiplexer only, they told, then You cannot say like this is a minimal switching function, I can't do this like that. No, it cannot. See, as per the design requirement, you need to work, that's it. So here what I am telling is, if the design is expecting in form of logic gates, then minimal switching function is preferable, is only the option. However, if they say they have multiplexer, which is a universal logic circuit or demultiplexer, and they are asking you to implement this function, then you need to convert this minimal switching function into standard SOP or POS. Okay guys, this one I can say that the standard SOP is needed if you want to implement the design in terms of combination circuits such as multiplexer, demultiplexers. Right guys, this is about question number 3. Let's enter the question number 4. Determine the connective asterisk for the Boolean variable x and y as x asterisk y is equals to xy plus x bar y bar. Let z is equals to x asterisk y. Which of the following expressions are correct? The expression for p, x is equals to y asterisk z. Similarly, y is equals to x asterisk z. X asterisk y asterisk z is equals to 1. Let us find out among the 3 p, q, r, which of the expressions are correct. Let's first of all p. If you take p, it is simply x is equals to y star asterisk z. Guys, if it is x asterisk y, it represents xy plus x bar y bar, isn't it? Yes. Now similarly here also y asterisk z, right? You can write in the same form, that is yz plus yz bar, y bar z bar. However guys, what is z? xy only, x asterisk y. What is x asterisk y? xy plus x bar y bar na. So we'll substitute here also, it is y into xy plus x bar y bar plus y bar into, guys, hope you know this is xy plus x bar y bar, which is x nor operation. If you take z bar, x nor whole bar will be xr only, hence you can write it as x bar y plus xy bar. Got it? Now when you simplify, it is xy, y into y bar 0, again y bar into y 0 plus x y bar. Now guys, if you take x as common, y plus y bar, hence it is x only, as y plus y bar becomes 1. Hence this statement, whatever y asterisk z is x only. Yes, true. LHS and RHS are equal. Now let us take the second one, y is equals to x asterisk z. Let's take this y now. Guys, here x asterisk z. What is z guys? X asterisk y only na. So x asterisk y. Now if you express in this format, it will be like x into xy plus x bar y bar plus x bar into this whole bar, so that you will get it like x bar y plus xy bar. It is a exclusive NOR operation. When you take complement, it becomes XOR operation. Hence we have written x bar y plus xy bar. Again when you simplify, you get xy plus x into x bar 0 plus x bar y plus x bar into x 0. Therefore guys, here the y is equals to, see here if you take y common, x plus x bar, it's 1 only na, then LHS equals to RHS. Even option Q, the expression Q is also true, that is y like x asterisk z is equals to y only. When you simplify, substitute, you will get at the end y only. Got it? And now let's see the last one, the r expression, that is x asterisk y asterisk z is equals to 1. Guys, here what is xy, guys? X asterisk y, that is z only now. Then why don't you substitute as it is here, that is z asterisk z. Now how you write as per this equation, that is z z plus z bar z into z only, z bar into z bar only, then z bar plus z bar is 1 only now. Hence we reached 1. So x asterisk y asterisk z is equals to 1 only. So guys, what we can say is, as per the question, the expressions p, q, r all are true only. Hence the answer is p, q, r are true. Okay guys, this is what here question number 4. In this way only, VLSI aspirants, especially I'm talking about you only, this YouTube channel is exclusively designed to give some encouragement to the VLSI students. Yes, we are exclusive to VLSI job aspirants only. Okay guys, in your interviews, in your placement examinations, you will get these kind of questions only. Okay, nested functions, function in Boolean algebra. Okay, let's dive into the question number 5. F of a comma b is equals to a bar plus b. Simplified expression for function f of x plus y comma z is. So we want to find out what is the expression for f of x plus y comma z is. Guys, they have given the sample function as f of a comma b as a bar plus b. Now let's find out this. Okay, that is f of x plus y comma y. As per this, how you can rewrite? Let's assume this is a, therefore x plus y whole bar plus b, which is y. Okay, now guys, if you rewrite, like simplify this, x plus y whole bar, it is x bar into y bar plus y. Now by using distribution theorem, you can rewrite it as x bar plus y into y plus y bar. Isn't it guys? Yes. So here you see this is y, so that x bar y bar, isn't it? Yes. Now here what is y plus y bar? 1. Then the simplified term is x plus y. Now you substitute in this case, that is f of, that is x bar plus y comma z. Okay, now this is a, this is b. Let's take this as a and this is b. Okay, now here as per this expression, how you can express? It is like x bar plus y whole bar plus z, isn't it? Yes. Now x bar whole bar, x into y bar plus z. Hence guys, here the nested functions in Boolean algebra, for this one function, the simplified form expression function is xy bar plus z, xy bar plus z. Okay, let's see another model. Question number 6. Let x be a 3 variable Boolean function that produces output as 1. when at least two of the input variables are 1. Which of the following statements are correct where A, B, C, D, E are Boolean variables? First of all, we need to get the function as per this given statement. What they told? The output becomes 1 when at least two of the input variables are 1. As per this, if you draw the truth table, how it becomes? Let's assume those variables are P, Q, R and this is X. Therefore, guys, here we get 000, 001, 010, 011, 100, 101, 110, 111. Now, at least two of the input variables are 1. Where it is possible? Here. Here output will be 1. Here output will be 1, 1, 1. And rest of the cases, output is 0. This. As per the given statement, the truth table is this. Now, as per this, if you get the simplified, minimized expression, what it is, let's draw a 3-variable corner map. It is like this. P, Q, R. P bar P, Q bar R bar, Q bar R, Q R, Q R bar. Now, as per this, guys, here this case, this one, this one, this one. P bar Q R, P bar Q R, P Q bar R, P Q R bar, P Q R. This one mapping is done. Now, if you simplify this, this and this, yes, we get the function. The simplified function is PQ plus QR plus PR. This is the simplified Boolean function as per the given statement. This is very important. Now, let us check one by one every option whether we are getting like as per the options whether we are getting the same LHS is equals to RHS or not. Let's see one by one. Let's see option 1. X of A comma B comma X of C comma D comma E is equals to X of A comma B comma C D comma E. Let's take LHS part. X of A comma B comma X of C comma D comma E. Got it? Now, if you compare this and this will be P, this will be Q and this will be R. Now, if you take this R, what it is? Again, as per this, it is CD plus DE plus CE. Now you substitute here. Therefore, you get this is as like X of A comma B comma this one CD plus DE plus CE. Now, if you again take this equation reference, then it is like AB plus B into CD plus DE plus CE plus A into CD plus DE plus CE. Now, when you expand the equation, we get like AB, BCD, BDE, BCE, ACD, ADE, ACE. This is LHS done. We want to take the RHS part, that is X of like again x of a comma b comma c d comma e. Now if you compare, this is p q, this is r. Now what is p as per this reference? Again this p is equals to AB plus BC plus AC. Got it? Now again if you take this expression as the reference with respect to this, then it will be like, it is PQ means PD plus DE plus PE, isn't it? Yes. What is P? AB plus BC plus AC. AB plus BC plus AC into D plus DE plus AB plus BC plus AC into E. If you have, like, if you write the expansion also, it is like ABD, BCD, ACD plus DE plus ABE plus BCE plus ACE. This one. So this is RHS, this is LHS. Is there any similarity? No. Hence the option A, LHS is not equals to RHS. Hence this is not a correct statement. Okay? ABC plus AB, ABC, AC. Now guys, here this is AB, 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 even ABC, ABC. So you take AB as common, then you will get AB. Now it is BC as it is, AC as it is. So we got AB plus BC plus AC, the LHS term, this one. Now let's see x of a comma b comma c. Guys, coming to the RHS term, if you take x of a comma b comma c, as per this expression, this will be P, this will be Q, this will be R. Then we can write down this as it is, so that it is AB plus BC plus AC. Now guys, LHS and RHS are equal. Got it? Hence the right answer is option B. So this statement is correct. Let's see the third one. Let us take the LHS part. Okay. So if I take, like, I can write directly here, this is P, this is Q, and this is R. For better understanding, guys, I have rewritten this x of P comma Q comma R is equals to PQ plus QR plus PR. As per this, guys, what is R? AC plus CD plus AD. Now if you take this as PQR, then x of P comma Q comma R as per this is AB plus B into R plus A into R. Again, it is like AB plus B into AC plus CD plus AD plus A into AC plus CD plus AD. Now if you expand the expression, AB plus ABC plus CD plus AD plus AC plus ACD plus AD. This is the expression. Okay, we will keep it as it is. Yes, you can simplify here. This is AB plus ABC. You can rewrite it as AB. Similarly, CD plus AD plus ACD, AC, ACD. Then you can rewrite it as AC. Again, if you take these two, you will get it as AD. Anyway, AD, so that it is AB plus CD plus AD plus AC. Okay, finally, this is the expression of LHS. Similarly, you take RHS. This is PQR. Then, what will be the expression of this? It is AB plus BA plus A. A into A is A only, right? AND operation means logical multiplication. Again, this CDC, this is PQR, hence it is CD plus DC plus C. Now guys, A is there, A into 1 plus B only, na, means A only. Again C common, then it's AC. RHEC is AC. LHS is this big equation AB plus CD plus AD plus AC. Hence, option C is also not true. Okay. Let's see the last one, D. LHS. Coming to the LHS, x of A comma B comma C. It's just like similar to x of P comma Q comma R. Hence, it will be like AB plus BC plus AC. LHS over. Now RHS. Coming to the RHS, it is P, Q, R. Then guys, what is Q? AB plus BC plus AC. What is R? AC plus CC means C plus AC. Means guys, it is C only now, isn't it? C if you take common. Now, if you write directly, it is like AQ plus QR plus AR. Now, it is A. Q means AB plus BC plus AC. QR means this. ABC plus BC plus AC. Again, AR. A means A into R. This one means AC. Now guys, when you expand, you get AB plus ABC plus AC. Again, ABC, BC, AC, AC. Now guys, here it's ABC, ABC. And again, here we'll write AB. Like this ABC, you take AB as common. You get AB as it is and AC plus BC. That's it. So anyway, AC is repeated. Now guys, you see this. Now LHS and RHS are equal. AB plus BC plus AC. AB plus AC plus BC. Hence guys, here we can say for this particular options, both B and D are correct statements. Okay guys, so these are the possibilities. We get the examinations, VLSI placement drives, these kind of questions only, right? So don't miss these kind of questions at any cost, right? We are going to discuss about Venn diagrams clearly. Okay, now if you take the expression, the Boolean expression A plus A bar B, what might be the Venn diagram? Guys, here two variables are there. Therefore, there will be two circles. In a Venn diagram, if there are two circles, it could be in this way, A, B. Let's discuss about SOP form, sum of product form. Therefore, remember guys, this area is A bar, B bar, because this portion is outside of the circles, right? So it is A bar, B bar, and this will be A, B bar, because it is related to only A, whatever the portion covered by the B, even though it is eighth one, we are removing it. Means here guys, this portion, let's select this. This is about AB bar. Similarly, this will be A bar B, and whatever the common portion, this will be AB. Okay guys, this is AB. Now this is about SOP form. Now let's take the Boolean expression, that is A plus A bar B. By using the distribution theorem, we can rewrite this equation as A plus A bar into A plus B. Isn't it? Yes. Here A common, A bar B you can rewrite. So A plus A bar B. So you are writing in this way. Now what is A plus A bar? 1. Then it will be A plus B only. So he is expecting A plus B. Remember guys, if it is A intersection B, that will be A into B, because the common portion, right, when both inputs are high, then only output will be 1. That means here A intersection B is A into B, A and B. Similarly, if it is A union B, then if any one of the input is 1, your output becomes 1, right? That is possible in OR operation. So it is A plus B. Okay, so we got A plus B means it is A union B. Therefore, in the Venn diagram, if you take with two variables, then the A plus B Venn diagram is this one, which is A union B, this one. Okay, so till now we have discussed about SOP, and remember guys, there might be POS also. Then if it is POS, how you will get it? Very simple. You know, max term is equals to min term whole bar, right? In the same way, here if you want to find out the max term here, you just simply apply bar. Therefore, here let us write here what you will get: A bar, B bar, whole bar. Then this will be A plus B, and this will be like A B bar, right? So A bar plus B, and this will be like A B whole bar, that is A bar plus B bar, and this will be like A plus B bar. That's it. Okay, so normally what I recommend is you just remember SOP form, and you just remember max term is simply complement of min term, so that automatically you can do the De Morgan's theorem. Okay, this is about a two variable Venn diagram, right? Let's see another example, this time three variable Venn diagram. Question number 8. What is the Boolean expression for the shaded area in the Venn diagram? Guys, here there are three circles, three variable. Now here whatever he selected the portion, from that you need to get the minimized expression, right? Before that you should know every corner what is the min term. Okay, now let's see a three variable Venn diagram. Let's assume A, B, C. Okay guys, now whatever the portion outside of these three circles will be like A bar, B bar, C bar, and the common portion A, B, C will be A, B, C. Okay now guys, now you take this portion where A portion is there, whereas B and C not at all like connected. Hence, this will be A, B bar, C bar. This portion is exclusive A, not at all common portion. Similarly, this portion exclusive to the B. Hence, it is A bar, B, C bar, and this will be A bar, B bar, C. Okay, now we want to see this portion. It is connected with the A, B variables, not at all C. Hence it is A, B, C bar. Similarly this, it is the intersection of A and C. B is nowhere connected. So it is A, B bar, C. And this will be BC. Hence it is A bar, BC. These are the min terms for this three variable Venn diagram. Got it guys? Now let's see this. As per the given question, this portion will be AB, C bar, and this portion will be ABC, and this will be A bar, B bar, C. Now if you assume that's a Boolean function f of A comma B comma C, then it will be like ABC bar plus ABC plus A bar, B bar, C. Now here AB common, therefore AB into C plus C bar becomes 1. So that AB plus A bar, B bar, C. This is the simplified Boolean expression for this particular Venn diagram. And one more thing guys, here if you want to represent in terms of POS, if they state you express the expression in terms of POS, then as usual you take the same, and here of course guys it is C bar. You just apply the bar here complement so that you will get the POS term. For example, I want to write it for A bar, B bar, C bar. You just take a bar, then A bar whole bar plus B bar whole bar plus C bar whole bar. It is A plus B plus C only. Got it guys? So in this way you can rewrite it. Let's see another model, question number 9. The Boolean expression for the shaded regions as shown in the figure is. Guys, as per the previous questions, we can say easily what about this and this. For example, the same diagram guys, I want to express in terms of SOP. At the same time, we will see from in terms of POS also. Okay, now usually we know very well in SOP expression wherever the output is 1, those min terms only we consider, isn't it? Yes. So for this Venn diagram, whatever the selected portion that you need to take. Okay, this will be A B bar and this will be A bar B, isn't it? Yes. So the Boolean expression f is equals to AB bar plus A bar B. So guys, you can say indirectly this Venn diagram is for XOR gate, isn't it? Yes. Similarly, now guys, I want to go with POS. I want to express the equation in terms of POS. And you know very well, in POS, we consider the max terms whose output is 0. So for this Venn diagram, you want to write POS expression. Then you need to choose the area where it is not selected. Where it is not selected? Here and here. If it is POS form, what it will be? Usually it is A bar, B bar, right? Then if you apply bar again, you will get A plus B. And this will be AB. If you apply bar, you will get A bar plus B bar. Hence, wherever in the Venn diagram, you need to choose the areas which is not selected. That is the important thing. So, here in POS, if I want to write the equation, F is equals to A plus B into A bar plus B bar. Right guys? This is a POS expression. This is SOP expression. Still, you want to make it equivalent, you cross check A into A bar, 0, A into B bar, AB bar, B into A bar, B, B into B bar, 0. So at the end, you got the same term, which is A XOR B. Of course, you know guys, this is the XOR equation in SOP form. This is also XOR logic gate equation only in POS form. Okay guys, we are going to discuss about duality in digital circuits. Yes, what is the importance of the duality, where we will use, and how to apply duality we want to know. Without any delay, let's dive into the question number 10. For the identity AB plus A bar C plus BC is equals to AB plus A bar C, what is the dual form? Guys, remember, dual form or duality is used to convert a positive logic system into negative logic system. That's only the reason why do you need duality. Okay, now how to convert one particular expression into a dual expression? That contains 3 steps. Step number 1, we need to replace AND with OR. Similarly, OR with AND. Okay now guys, for better understanding you can remember in this way. Dot can be considered as plus, plus can be considered as dot. In fact guys, in digital electronics, we need to call this dot as AND operation. This is OR operation. Strictly speaking, you should not speak dot plus also. If you say into plus, it comes under arithmetic operations. Okay. Now, the second one, in your expression, if 0 is there, you need to replace with 1. If you have 1, you need to replace with the 0. And the third one, important one, keep the variables as it is. You should not change the variables. That means, suppose in your original expression, there is A bar. Then you need to keep it as it is. A bar only. You should not take instead of A bar, A like that. No. So these are the rules to be followed to convert an expression into dual of that particular expression. Now, let's see this. Now here, A dot B is there. Then how to write? A plus B into, because plus is there, into A bar plus C into B plus C is equals to A plus B into A bar plus C. That's it guys. This is what? Dual expression of that given expression. Got it? And guys, you know very well, for any function, if you apply dual 2 times, then that will be equal to f only, the same function. However, there is one self-dual function. Okay, coming to the self-dual function, for this function, if you apply one-time duality, it will be equal to the same function only, means fd is equals to f only. This is called self-dual function. Moreover guys, here if you take example, let us take example, that function is AB plus BC plus AC. If you apply duality, then you get A plus B into B plus C into A plus C. Got it guys? Now when you simplify, here you apply distribution theorem, this one, B plus AC, isn't it? And you write this A plus C only. Now you multiply AB, BC, AC, AC. Now guys, AC two times, you can write AC only. AB plus BC plus AC only. See this. Hence what I mean is, for a particular function, if you apply one-time duality, if you get the same function, that function is called self-dual function. Okay? And you know, for n variables, what are the self-dual functions? It follows 2 power n minus 1. For n variables, the self-dual functions are 2 power n minus 1. The same duality you can apply logic gates also. For example, let us take AND gate. The operation is AB. Let's consider this logic gate. Then you apply duality for this, what you will get? A plus B only. So that it will be like this. Hence, guys, the duality of AND gate is OR gate only. Similarly, you apply OR gate for this OR gate duality, you will get AND gate only. So you can remember one more point saying that the duality of AND gate is OR gate only, the duality of OR gate is AND gate only. The same you can consider the NAND gate also. For example, it is AB whole bar, this one. Now here if you apply the duality, what you get for this function? You get A plus B whole bar only, na? We need to keep the variables as it is. Simply you need to change AND with or with AND. That's it. Therefore, here you get NOR gate, isn't it? So, the NAND gate duality is NOR gate. The NOR gate duality is NAND gate. Yes, these are the duality of the particular gates. Hence, here guys, we can say, even you may be getting a doubt saying that, sir, where you get 0 as 1 or 0, you are getting the expressions only, na? So why are you mentioning there? No, you cannot say the function looks like A, B, C or anything at all. It could be like, for example, let us take here A bar into A is equals to 0. This is the function. Now they are asking what is a duality for this. Simply you need to keep the variables as it is. Replace AND with OR, replace 0 with 1, 1 with 0. Therefore, it is A bar plus A is equals to 1 only. So, you need to remember all these 3 points if you want to apply duality. Got it? And finally, why do you need duality? So, I told you already here guys, the duality is used to convert a positive logic system into negative logic system, a negative logic system into positive logic system. In the simple way, you can tell even in this way as well. Suppose your design is in terms of SOP, sum of product form, but the designer, the client is expecting the POS form, product of sum form. Then you apply duality. That's it. Therefore, this SOP, active high output, can be converted into active low output, which is POS. This is the importance of duality. Okay guys, so like all these are very small like topics which influence big impact when you go to applications part. Okay guys, this is about duality, complements in detail. Okay, without any delay, let's dive into the question number 11. Consider the following Boolean expression: f is equals to x plus y plus z into x bar plus y into y bar plus z. Which of the following Boolean expressions are equivalent to f bar? Guys, here f bar is complements. Sometimes they say f dash or fc, like this. All are same only. Okay, it represents complement of the Boolean expression. Now guys, here first of all, how to get complement of the given expression we want to know. That contains 3 rules. We need to follow 3 rules. They are: you need to replace AND operation with OR operation, similarly OR operation with AND operation, and 0 must be replaced by 1, 1 must be replaced by 0, and the third one, that is complement the variables. This is the difference between the complement and duality. Remember guys, and the rest of the 2 are same only in duality and complement, but whereas here in complement the third one is different, that is complement the variable. In given expression it is a bar, take it as a. It is b, take it as b bar. That's it. If you follow these 3 rules, we can get complement of the given expression. Let's try. Guys, the given expression f is this. Now let's take f bar, that is x bar, y bar, z bar plus x y bar plus y z bar. Isn't it guys? This one. So it is as it is matching with the first expression. So this is true. The f's complement is this one only. Yeah, this is true. Similarly, you take the second one. Here x bar complemented, but plus as it is there. Hence even you check the remaining maxims also. The plus is as it is. Hence this is false. Now you take the third one, the c, x plus z bar into y bar plus z bar. Now guys, you take this given expression. Now here y bar is common, therefore you can take y bar as common, x bar z bar plus x plus yz bar. Again here you can use distribution theorem, a plus bc. How you can write a plus bc? Like a plus b into a plus c. Therefore, according to this distribution theorem, we can split here like y bar into x plus z bar into x plus x bar. Again y z bar. Okay guys, now x plus x bar becomes 1, hence it is y bar into x plus z bar plus yz bar. If you expand, you will get like y bar x, y bar z bar, again y z bar. Here you can take z bar as common, then it is y bar plus y na. Y bar plus y gets cancelled, becomes 1, then it is z bar plus xy bar. This is the minimized expression. Now it is in option D. Hence xy bar plus z bar is also the right answer, isn't it? Yes. And with the same distribution theorem, you can rewrite this. How? Like this. That is z bar plus y bar, z bar plus x. Hence guys, for the given Boolean function, the complement of the function is equal to A, C, D. All these three options are equivalent to complement of the Boolean function. Okay, so this is what complement of the Boolean function. Let's see another example. Question number 12. Match list 1 Boolean logic function with list 2 inverse of function. You know guys, inverse of the function, complement of the function, all are same only. Okay, coming to the rules to be followed. You need to replace AND with or with AND. 0 with 1, 1 with 0, and you need to complement the variables. Okay, so if you apply those like rules for these given functions, accordingly we will get the complement, the inverse of the function. Okay, let us take C, A plus BC. For this complement, A bar dot B bar plus C bar. Therefore, if you expand A bar B bar plus A bar C bar, isn't it guys? Even we get the expression as it is, see here. Hence, C2. Now, you take the B, AB plus A bar B bar plus C bar. How you get? It is A bar plus B bar into A plus B into C. That's it guys. Now if you multiply A into A bar 0, A bar into B, A bar B, B bar into A, B bar A, B bar into B 0, C. A bar B plus AB bar is XOR operation only. A XOR B into C. That's it guys. So as per the options, B 1 only, isn't it? Yes. Now if you take the D, it is directly applicable. You see here, if you apply the complement A into B into C, A B C, A bar into B C, A bar B C, A bar like A B C bar, A B C bar, hence D3. And finally guys, we have the last one, AB plus BC plus CA plus ABC. Now if you apply the complement directly, we get A bar plus B bar into B bar plus C bar, C bar plus A bar into, even guys here ABC is there. You can take any one of that common. Suppose let's assume this. It is CA plus ABC. You take AC common, then 1 plus A. It's 1 only. So CA. You can keep it as it is. Now, you see in the options, it is in the SOP form only. Normally, if you take the complement in this way, you get the POS form. Yes, but that is not in the options. On options, it is in SOP form. Hence, you need to multiply, you need to expand this again. Now guys, you see these two. This is B bar common, right? So, you can take A bar C bar by using distribution theorem. B bar plus A bar C bar. Got it? Again here A bar plus C bar. Now you multiply A bar B bar, B bar C bar, A bar C bar, A bar C bar. So 2 times it has come, so you can take it as 1. A bar B bar, B bar C bar, A bar C bar. Hence guys, here the right answer is this. So I can say A 4, A bar B bar plus B bar C bar plus C bar A bar. Guys, here complement of the functions. Even you need to know some important points. For example, let us consider a 3 variable Boolean function sigma m of 0 to 3 7. Let's assume this is the Boolean function. For this function we applied one NOT gate. Suppose if this is the one and we applied a NOT gate. Now here what will be the output? See, as per the expressions, yes, you can do, this is only the procedure. However, remember, suppose they have given the minterms and that function is applied to the NOT gate, what will be the output? Means in terms of minterms, remember everybody, that is y is equals to sigma m of, guys, you know NOT gate 0 becomes 1, 1 becomes 0, therefore it is sigma m of their product terms, whatever the missing you write down, 1, 4, 5, 6, that's it guys. So this is what here, say y is equals to sigma m of 0, 2, 3, 7 given to a NOT gate, the output will be the minterms only, but whatever the missing terms you will get it here. Okay guys, so this is what here the Boolean function and inverse of the function. Got it? We are going to discuss about a best hack which is very important, frequently asked question in all VLSI placements examinations. Without any delay, let us start question number 13. There are 4 Boolean variables x1, x2, x3, x4. The following functions are defined on sets of them. F of x3, x2, x1 is sigma 3, 4, 5. G of x4, x3, x2 sigma 1, 6, 7. H of x4, x3, x2, x1 is equals to f into g. Then h of x4, x3, x2, x1 is 0 or sigma 3, 12, 13 or 3, 4, 5, 1, 6, 7 or 3, 12, 15. What is the right answer? Guys, first of all, we need to find out the minterms respecting to this particular numbers. Okay, so let's enter into the solution. If it is x3, x2, x1, then 3 will be 0, 1, 1. Hence, it is x3 bar, x2, x1. And again 4 means 1, 0, 0. Hence, x3, x2 bar, x1 bar. Again 5, 1, 0, 1. Hence, x3, x2 bar, x1. This is the expression for f. Okay. Similarly, what is g? Coming to the g, it is x4, x3, x2. It's a 1, 6, 7. 1 means 0, 0, 1. Therefore, it is x4, x3, x4 bar, x3 bar, x2. Similarly, x4, x3, x2 bar. Again 7. It's x4, x3, x2. Okay. Now what they told, h of x4, x3, x2, x1 is equals to f into g. Let's multiply f into g. We get x3 bar, x3 bar. Like these two terms gets multiplied. Then guys, x4 bar, x3 bar, x2, x1. Again, this term with the second. x3 bar, x3, 0. x3 bar, x3, 0. So, with the second two terms gets cancelled. Becomes 0. Again this one. x3, x3 bar, 0. x3, x3. So, it will be like a x4, x3, x2 bar, x1 bar. Again, this with this one, x2 bar, x2, 0. Now the third one, here x3, x3 bar, 0. This and this, x4, x3, x2 bar, x1 plus again here x2 bar, x2 becomes 0. Hence the f multiplied g, the expression is this. Finally we got this. Now this will be equal to h only. Hence in terms of h of x4, x3, x2, x1, what will be the min terms? See, f into g is h only. So h of x4, x3, x2, x1. Accordingly here you say this. It is 0, 0, 1, 1 means 3. 1, 1, 0, 0, 12. 1, 1, 0, 1, 13. Hence guys, the right answer is option B. Sigma of 3, 12, 13. Guys, mainly they focus on either simplification or modification. They take two different functions and they'll expect the merged version of both of two. Okay guys, you can expect these kind of questions very sure. Don't miss these kind of hacks in VLSI placement examinations. Okay, we mainly focus on logic optimization, how we can design a simplified circuit as per the design requirement. That's it. Let us dive into the question number 14. The black box in the figure shown below consists of a minimum complexity circuit that uses only AND or NOT gates. The function f of x, y, z is equals to 1 whenever x and y are different and 0 otherwise. In addition, 3 inputs x, y, z are never all the same values. What is the equation that leads to the correct design for the minimum complexity circuit? Right. It is a design which with 3 inputs. Right. So as per the design requirement, you need to determine the truth table. This is a crucial step in the question. Remember everybody. So as per the requirement, if you determine the truth table, how it looks? See, there are 3 variables. Therefore, x, y, z. And this is the function. Let's assume. Therefore, guys, here we get 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Now, what is the requirement? Design requirement. F of x, y, z is equals to 1 and x and y are different. When x and y are different, guys, here, because x, y here 0, 0. X and y are different in this case, so you will get 1. Here also 1, 0, you will get 1. Right? And 0 otherwise. However, there is one more requirement. In addition to that, the 3 inputs x, y and z are never all the same values. So they never all the same values they told. If it never happens, it could be considered as don't care. Hence, this will be don't care. This will be don't care. All are the same values now. And remaining won't happen and that is equal to 0. That's it. So guys, the first crucial step completed. We determine the truth table as per the design requirement. Now what next? What next? You take the min terms and you give the expression? No. Because he is asking you the minimum complexity circuit. Hence, you need to map this into the K-map. You need to simplify the expression and then you need to develop the hardware as per the equation. That's it. Hence, now if I take the 3 variable K-map, we get like this. It is like x, y, z. Hence here x bar x, y bar z bar, y bar z, y z, y z bar. Now guys, here where we got, see this 0, 0, 0, don't care. 1 1 1 don't care. Now it is 0 1 0 2 means 0 1 2 here 1. Similarly 3 here 1. Again 4 5 here 1 and 1. That's it. So we mapped it. Now you simplify. When you simplify this one, what do you get? This is x. Z bar gets cancelled, y bar. Similarly this one. What is this? X bar y. Hence guys, the Boolean function as per the design requirement, the minimum complexities are cured. The simplified equation is xy bar plus x bar y. These kind of questions are essential questions. Definitely you will get the questions, these kind of things in all VLSI placements examinations. Remember guys, don't miss these kind of conceptual based questions. Okay, we are taking one example and explains how logic optimization can be done, because you know guys, VLSI means design optimization. You need to implement the design with less amount of hardware, isn't it? Yes, without any delay, let's dive into the question number 15. Let x is equals to x1 x0 and y is equals to y1 y0 be unsigned 2-bit numbers. The function f is equals to 1 if x greater than y and f is equals to 0 otherwise. What is the minimized SOP expression for f? That's it guys. Whatever you are watching here, the red color one is the question. That's it. Now we want to get the minimized SOP expression. What is the design requirement? The design requirement is f is equals to 1 if x greater than y, otherwise f is equals to 0 only. Now guys, here x is equals to x1 x0, y is equals to y1 y0. They are unsigned 2-bit numbers only. Hence here, as there are 2 plus 2 4 variables, then we will get 16 combinations. To optimize the time, I have written the truth table combinations already. Okay, now let's enter into the design requirement. When f is equals to 1, if it is x greater than y, so in these cases x is 0 only, hence output is 0. In this case also 0 1, it is 0 0. Now x is greater than y, and remaining all the cases here it is x less than y only, hence all zeros. Again here x is greater than y, here x is greater than y, here x is equals to y, here x less than y. Similarly here 1 1 0 0, x is greater than y, here x is greater than y, and here 1 1 1 0, then obviously it is x greater than y, and this one x is equals to y, then it is 0. This one guys, hence now if you see what are the minterms, then obviously this is 4 and this is 8 9 and 12 13 14. That's it. These are the minterms. Hence if you map into the SOP like a K-map, because we are expecting SOP expression, if you map them directly, you know guys, this is 0 1 2 3, this is 4 5 6 7 8 9 10 11 12 13 14. So we mapped. Now let's simplify. If you simplify the expression, see this is one quad. If you simplify, what you get? x1, x0 bar gets cancelled, y0 bar gets cancelled, so it's a y1 bar, x1 y1 bar. Again there is a pair here, so that it is x0, this one y1 bar, y0 bar, and here there is a pair. Therefore, here you get like x1, x0, and this y1 bar gets cancelled, it's a y0 bar. Hence guys, the minimized SOP expression as per the design requirement is f is equals to x1 y1 bar plus x0 y1 bar y0 bar plus x1 x0 y0 bar. This one guys, this is the minimized expression. In this way, if it is a big logical expression as per the requirement, you can minimize the design. Okay, we are taking another numerical on logic optimization, design optimization. VLSI means optimization, remember. Let's dive into the question number 16. A logic circuit implements the Boolean function f is equals to x bar y plus xy bar z bar. It is found that the input combinations x is equals to y is equals to 1 can never occur. Taking this into account, what is the simplified expression f? So as per the design requirement, you need to get the expression and then you need to simplify using K-map. That will be the simplified expression. So it is always two-step procedure. Step 1, as per she told, you need to get the truth table and you need to map it to the K-map, simplify it. That's it, step 2. Okay, now let's consider f value. Guys, it is in simplified form, but if you want to write in the truth table format and all, it might be in standard SOP only now. Hence, here the extra step is, as he has given the minimized expression, you need to convert into min terms fashion. Okay, therefore f is equals to x bar y. You know very well, you can add here z plus z bar, which is 1, plus xy bar z bar. Now guys, here x bar yz, x bar y z bar plus xy bar z bar. Now guys, what is this? 0 1 1 means 3, 0 1 0 means 2, like 1 0 0 4. This is sigma 3 2 4. Is that? Can we go to K-map? Can we simplify? No. Wait. One more is there. That is, it is found that input combination x is equals to y is equals to 1 can never occur. Never means, guys, this whatever x is equals to y is equals to 1 combination can be treated as don't care conditions. Yes, let's form the truth table x, y and f. It is like x, y, of course, z also, no? X, y, z. It is like 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0, 1 1 1. Now here what he told, 2 3 4, 2 3 4, and one more, x is equals to y is equals to 1 never occur. See here, x is equals to 1, y is equals to 1, x is equals to 1, y is equals to 1. These conditions never occur means they considered as don't cares. And remaining will be 0 as usual. Okay, usually in BTech academics etc. they'll give directly the minterms and the don't care conditions. Sigma is equals to 2 3 4 plus sigma d is equals to 6 comma 7, like that you can expect. But in VLSI industry, especially placement examinations, will get the full theory, lengthy question. But once you understand the question, the solution looks damn simple. Yes, they'll see your problem solving skills. Remember guys. Okay, now we got the truth table. Done. Let's map into the K-map. It's a 3 variable K-map. Therefore, you can write in this way, where the variables are x, y, z. It's x bar x, y bar z bar, y bar z, y z, y z bar. Now guys, here it is 2, 3, 4 now. This is 2, 3, 4. What about don't care? 6, 7 means this is 6. This is 7. This one. Now guys, we want to simplify it. How you can simplify? You take this quad, therefore x bar gets cancelled, z bar gets cancelled, y. And you can take this pair. Therefore, it is like x, z bar, y bar gets cancelled, z bar. Therefore guys, the simplified expression f is equals to y plus x z bar. Okay guys, for this design requirement, the simplified expression is this. And I suggest you please solve these kind of questions, n number of questions. It helps you how the design is getting minimized. Okay, we are going to discuss about literal counts. What is meant by literal count, how to calculate and all, we will clear. Let's dive into the question number 17. The literal count of a Boolean expression is the sum of number of times each literal appears in the expression. For example, the literal count of xy plus xz is 4. 1, 2, 3, 4 is 4. Okay, so it is literal count. It means it is the sum of the number of times each literal appears in the expression. Right? Now the actual question starts. What is the minimum possible literal counts of POS, product of sum, and sum of products respectively of the functions given by the following K-map? This one. Here x denotes don't care. So guys, now he has given the K-map, and here you need to calculate the literal count for POS, literal count for SOP as well. Okay, now let's start with SOP. You know very well guys, if it is SOP, we will take once only, of course, in addition to don't cares as well. Now let us take this. There is a 4 variable K-map. This. Now the representation like this is xy, zw. Obviously this becomes x bar, y bar, x bar, y, xy, xy bar. Similarly, z bar, w bar, z bar, w, zw, zw bar. Okay. Now, guys, here, wherever ones and x's, we need to consider them. X, 1, 1, 1, x, 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 1, x, x. So, we excluded zeros, we took logic ones and don't cares. Now, we need to simplify this. Here, you can take one quad in this way. Therefore, x bar x gets cancelled, y bar, and these two. Z bar gets cancelled, w bar, y bar, w bar. Similarly, here you can take one pair because you don't have any other option. Hence, here it is x bar, w, z bar. Again here guys, one more pair, and this will be xy, z bar. This one, hence I can say that the SOP expression is f is equals to xy z bar plus y bar w bar plus x bar w z bar. Now count how many literals here. 1, 2, 3, 4, 5, 6, 7, 8. 8 literal counts are like 8 literals are there, so that the literal count will be 8. Okay. So again take one more K-map, this time with POS. Now here it is a 4 variable K-map. Then here the representation is like this xy zw. Here what you get? X bar y bar whole bar you get. Then it is x plus y. Likewise x plus y bar, x bar plus y bar, x bar plus y. Similarly here z plus w, z plus w bar, z bar plus w bar, z bar plus w. This one. Okay. Now let's take only like max terms and don't care, means exclude min terms, logic one. That's it. Now you get here it is a don't care, here it is 0, 0, don't care, 0, don't care, 0. Here again this one, this is 0, 0, and it is don't care. Yes. Now guys, let's simplify. Here there is a quad, isn't it? Yes. Therefore it is z bar plus w bar, and again here there is a quad. Therefore here you get x bar plus y. Now what else? Here guys we have one more quad here, isn't it? Yes. Therefore you get x bar gets cancelled, y bar. Again here z bar plus z bar. Now guys we have only one left over, this one. Hence here what we can do is we will take here this pair. Now guys what we get here? Y bar gets cancelled, it is x plus z plus w, this one. So now guys finally the expression looks like f is equals to z bar plus w bar into y bar plus z bar into x plus z plus w into x bar plus y. This is the POS expression. Now what is a literal count? You just count it. 1, 2, 3, 4, 5, 6, 7, 8, 9. Hence the POS expression literal count is 9. SOP expression literal count is 8. We did already. It is like 1, like here only 1, 2, 3, 4, 5, 6, 7, 8. This one. This is about the literal count. Literal count is simply the sum of number of times appeared in the expression. Right? We are going to discuss about the number of literals count model. It's a very interesting and must needed question for VLSI placements. Okay, without any delay, let's enter into question number 18. Consider a Boolean function f of w, x, y, z such that f of w, 0, 0, z is equals to 1. Similarly, f of 1, x, 1, z is equals to x plus z. F of w, 1, y, z is equals to wz plus y. Determine the number of literals in the minimized SOP expression of f. First of all, you need to know about what is meant by literal count. The literal count is simply how many times each literal appears in your Boolean expression. That will be literal count. For understanding purpose, I have written the note, but remember the question is red color one only. Okay, literal count is the sum of number of times each literal appears in the expression. Suppose, for example, let us consider x y plus x bar y plus x y bar. For example, let's consider this. Now, in this expression, what is the literal count? 1, 2, 3, 4, 5, 6. The literal count is 6. The sum of number of times each literal appears. That's it. If it repeats also, you need to count. 1, 2, 3, 4, 5, 6. 6 is the literal count. So now for any numerical, if they ask us literal count, you need to get the expression, simplified expression. From that you can count so that you can tell. That's it. Now let's see the design requirement. The design requirement is this. Now f of w comma 0 comma 0 comma z is equals to 1. That means what? As per the given requirement, this is x only, this is y. So whenever x is equals to 0, y is equals to 0, output will be 1. That is a design requirement. Where x is equals to 0, y is equals to 0, here, again, here, here, even here also, and that's it. X, y, zeros in every, like nowhere it is like x is equals to 0, y is equals to 0 condition other than this. Now in these cases, take the output as 1. Hence guys, this is 1, 1 and 1, 1 over. First one is done. Now the second one. Here it is w, it is y as per this. Now whenever w is 1, y is 1, the output is x plus z. This one, where w is 1, y is 1, here you see w is 1, y is 1 means here. W is 1, y is 1. W is 1, y is 1. W is 1, y is 1. These are the cases, isn't it? Yes. In this case, it is x plus z only. Now in this case, x plus z in the sense this and this. 0 into 0 plus 0, 0. Again, this 0 plus 1, 1. And this 1 plus 0, 1. 1 plus 1, 1. This is also done as per the requirement. This is also done. Now the last one, f of w, x, y, z. Whenever x is 1, the output is wz plus y. Where we got x as 1, here x as 1 here. These are the cases, isn't it? These are the cases. Moreover, here also, this one and this one, x is equals to 1. These two combinations also. Yes, because x is equals to 1 only here. Yes. Now let's see the outputs. What is that? wz plus y. So here wz 0 into 0, 0 plus 0, 0. Again here 0 into 1, wz only 0 into 1, 0, 0 plus 0, 0 only. Again 0 into 0, 0, 0 plus 1, 1. Again 0 into 1, 0, 0 plus 1, 1. Again here 1 into 0, 0, 0 plus 0, 0. This one 1 into 1, 1, 1 plus 0, 1. Again this 1 into 0, 0, 0 plus 1, 1 only. Keep it as it is. Similarly here, w into z, 1 into 1, 1, 1 plus 1, 1 only. So now guys, it is like the finalized truth table. We got the truth table finally. Now what next? What next? Simplification. You need to map into the K-map and you need to get the simplified expression. In that simplified expression, we want to determine the literal count. Now, as it is a 4 variable, let us consider 4 variable K-map. This, where we get wx, yz, wx, yz. So the sequence like w bar x bar, w bar x, wx, wx bar. Similarly, y bar z bar, y bar z, yz, yz bar. Now guys, if you write down the minterms, what we get? The minterms guys here, sigma m. Let's consider f only. That is sigma m. The numbers 0, 2. Again, this one. What is this? 0, 1, 1, 0. 6, 7, 8, 9. Again 1, 0, 1, 1, 11, and again 12, 13, 14, 15, 13, 14, 15. Yes, these are the minterms. Yes, however guys, here there is a speed breaker. What is that? You see all the combinations are filled except 2. That is 0, 0, 1, 0 combination, 0, 0, 1, 1 combination, not there. It means it never occur. That condition never occur. If that condition never occur, it can be treated as don't care. Hence, it can be written in terms of don't care. So that guys, here plus sigma d is into 2, 3. 2, 3. That's it. We got now the minterms in addition with don't cares. Now map into them so that 0, 1, 2. Again, it is like 0, 1. Oh, sorry guys, this is 1. 0, 1. And this will be don't care. 3, don't care. Again, here 6, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. This one. Now, here you can take one quad here. And again you can take one quad here, isn't it? Yes. Therefore, this is the quad. What is that guys? W bar gets cancelled, x. And this, y. Again this, w and z. Now guys, here, as per like if you take the don't cares, instead of that, you can take here one quad, because if you take the quad also, but these two will be left over now. Hence you take these two. Then what is the expression for this quad? W bar gets cancelled, x bar, and this y bar, x bar, y bar. Hence guys, finally the minimized expression is f is equals to, or else let's write here, f is equals to x bar y bar plus wz plus xy Got it, guys? So there are 3 quads. Now let's count the literal count. 1, 2, 3, 4, 5, 6. Hence guys, for this question, the literal count is 6. 6 is the answer. In this way only, which is including with respect to the minimization, logic optimization. Definitely you can expect these kind of questions. Okay guys, the minimized Boolean expression for the given design requirement. Okay, let's dive into the question number 19. For the truth table given in figure, the minimized Boolean expression is, guys, this is the truth table. They have given the requirements in terms of truth table, right? Now, as per this truth table, what is a minimized expression we want to find out? It's very simple. Just map into K-map and get it. That's it. Now, as it is a 3 variable K-map, let's consider a 3 variable K-map, right? Therefore, we get the expression, we get the mapping in this way. It's x, y, z. This is x bar, x, y bar, z bar, y bar, z, yz bar. Now guys, see here, it is 0, it is 2, 4, it is 5, and it is 6. Midterm 0, it is 3, 5, 6. 0, 3, 5, 6 is the midterms. Fine. If you take them here, 0, 1, 2, 3. Again, 4, 5, 6, 7. This one guys, can we minimize this? No, you cannot minimize. Because it is already in the minimized form. You cannot minimize further. That's a twist in this particular question. That's the reason I have given you the options to you. Right? Easily, if it is the question, you people can write this one, this. But here options are there. You need to choose the correct option. How? So here you cannot minimize further. That's leave it. This. Now if you write the expression, then it is output P is equals to x bar, y bar, z bar, x bar, yz, x, y bar, z, x, yz bar. This one guys, is this in the options? No. Then how you can do that? We need to rearrange the terms. Remember guys, here we are not doing any optimization, but we are rearranging the terms in such a way that you will land into any one of the option. Yes, that's what our motto in this particular question. Now you see guys, here x bar is common. Let's take x bar. It is y bar z bar plus yz. Again, x common, y bar z, yz bar. Right. Now guys, here this can be written as x bar, y bar z bar plus yz. It is x NOR operation only now. Hence, why don't you write here y XOR Z whole bar. You can write y XOR Z also. Here we are taking as per the expression because here we have y XOR Z. Hence, it is like x into y XOR Z. This one guys. This is the one. Let's consider here y XOR Z as lump sum S, y XOR Z. Now guys, what is the expression? It is like x bar S bar plus xs. It is a XNOR operation only, na? Hence, how you can write x XOR s whole bar, because that is XNOR only, na? Now, what is s, guys? Why XOR z? Hence, you can write here p is equals to x XOR y XOR z whole bar. This one. See here, guys. So, as per the options, the right answer is option B. P is equals to x XOR y XOR z whole bar. This one, guys. These kind of questions beyond our imaginations. We all think, come on, let's so do it. No. There are some questions in this model also. Okay, guys. Again, we are concentrating on logic optimization, but this question is Babka all the questions. Yes, from my opinion. Okay, let's see question number 20. The truth table for the function f of a comma b comma c comma d is equals to sigma m of 0 comma 1 comma 3 comma 4 comma 8 comma 9 is. There's a truth table. Yes, where w x y z are given by d is a complement of the d. Now we want to find out what is w, what is x, what is y, what is z. Guys, the best part is here, it is a 4 variable Boolean function, but he has given 3 variable truth table. In terms of true variable, 3 variable truth table. So it's a big deal. We want to find out what is w, what is x, what is y, what is z. Usually, guys, for example, let us take 2 variable K-map or truth table. It is, let's assume f. Now it is 0 0 0 1 1 0 1 1. Usually if I say like this, then what will be the expression, guys? Like f is equals to a bar b bar plus a b bar. This is the expression only, na? Isn't it? Yes. Exactly speaking, do you know what is the exact expression? That is f is equals to a bar b bar into 1, because 1 is there, na? Similarly, this one a, even you can take this as well, that is a bar b into 0. Similarly, a b bar into 1 plus a b into 0. Anything into 0? 0. Anything into 1? Anything. That's why you got the same. See here. This is the pattern, remember. As per this, here if you take the expression, that is f is equals to, guys, that is 0 0 0 means a bar b bar c bar w plus a bar b bar c x plus a bar b c bar y. Anyway, into 0 becomes 0 only, na? Then you take this one, that is a b bar c bar z. We got the expression. Now, as per the minterms, let's minimize the expression. Now, it is a 4 variable K-map. Therefore, it looks in this way, where we have a, b, c, d. Therefore, it is like this: a, b, c, d. C bar, d bar, c bar, d, c, d, c, d bar. Again, a bar, b bar, a bar, b, a, b, a, b bar. Now, guys, as per the minterms, 0, 1, 2, 3, 4, that's it, 5, 6, 7, 8, 9. That's it. Now guys, we want to simplify it. Yes guys, suppose if I simplify, let's take this one and this quad, then you will get here one pair, here also you get one pair, then you will get 3 terms only, na? Isn't it? 3 min terms only you get it. However, we have 4 terms now. So for that reason, what you can do is you can go with trial and error as per the options and all. Here what we can say is, let's take this is a pair, this is a pair. Now you take this as it is single and single. It's completely as per the options, remember, right? Now guys, if I take this, what I'll get? This is A bar, B bar, C bar. This A bar, B bar, C D. And this A, B bar, C bar. And this A bar, B, C bar, D bar. Now we got 4 terms. Now you compare. Here, let's take A bar, B bar, C bar. Where we got A bar, B bar, C bar? Here. Okay, here what you get guys? This means A bar, B bar, C bar. Okay, here guys we have A bar, B bar, C bar. And here W. Then if you compare this and this, what might be the W guys? 0 only. Sorry, W is 1 only. Whenever W is 1, then you get this expression only, na? Hence, W is 1. Okay, W is 1. Similarly, A bar, B bar, C. Here, A bar, B bar, C, D. Then what is X guys? Obviously, it is D only. X is equals to D only. Similarly, A bar, B, C bar. A bar, B, C bar. This and this. Now guys, what is Y? D bar. Y is equals to D bar. They said small d is a complement of capital D. D bar. Hence it is small d. And finally Z. What is Z? A, B bar, C bar. See, A, B bar, C bar. Then it is Z. Then Z must be 1 only. Z is equals to 1. So in this way guys, it's completely options based as per the requirement. Here we design the hardware in such a way that it is a 3 variable, but he has given in terms of 3 variable. It's a 4, he has given in 3 variable, right guys? So in this way, these like in VLSI placement examinations or even interviews as well, please don't assume the VLSI interviews will be like only some 15 minutes or 20 minutes or 30 minutes. No, it is not like that. It minimum of minimum, there will be 1 hour interview. Remember, if you are very good, then they'll take you to 1.5 hour, 2 hours also. If you are good, if you are not at all competent, then minimum they will take 1 hour. Okay guys, so this is what here the best hack in Boolean Algebra and K-Map, right? Let's have another model, especially nested functions. Okay, let's see. A 3 input majority gate defined by the logic function m of a comma b comma c is equals to ab plus bc plus ac. What is the logic gate represented by the function m of a comma b comma c whole bar comma m of a comma b comma c bar comma c. So this is the function and this is a nested function, a function inside the function. Okay, are you ready? Yes. Without any delay, let's start. Before going to proceed into the solution, we want to know about m of a comma b comma c whole bar. What it is guys? See, it is like AB plus BC plus AC, right? Then whatever you take this m of a comma b comma c, It is like AB plus BC plus AC whole bar. Then guys, you can rewrite it as AB whole bar into BC whole bar into AC whole bar. Okay? So this is what m of a comma b comma c whole bar. Similarly, we have m of a comma b comma c bar. For this guys, here in place of c we got c bar. Hence, here also we can put in place of c bar, that is AB plus BC bar plus AC bar. Okay guys, fine. Now let's dive into the solution, actual solution. This is what here m of like this. So let's write it, m of, what is this? You can see there, AB whole bar into BC whole bar into AC whole bar, comma. This one, what it is? AB plus BC bar plus AC bar, comma, C as it is, C as it is. This one. Now, as per the given function, you can rewrite. See, this can be treated as A, B and C. As per the function AB, right? So, this one into this, that is AB whole bar, BC whole bar, AC whole bar into this one, AB plus BC bar plus AC bar plus B into C, that is AB plus BC bar plus AC bar into C plus again here this AC, that is AB whole bar into BC whole bar into AC whole bar into C. Okay guys, this is the finalized function. Here if you see this term and this term, AB whole bar, BC whole bar, AC whole bar is common, right? So we are writing this as common, AB whole bar into BC whole bar into AC whole bar. This AB plus BC bar plus AC bar into, like it's a plus, C, and the second term as it is, that is this one, AB plus BC bar plus AC bar into C. Okay, this function as it is, this one. Now guys, here we want to know what it gives the simplified expression. Let's do this. AB plus BC bar plus AC bar plus C. Using distribution theorem, you can write this as AB plus BC bar plus A plus C into C plus C bar. Anyway, C plus C bar becomes 1. Therefore, it is AB plus BC bar plus A plus C. Now guys, here A is common. A into 1 plus B plus BC bar plus C. Now it is A plus BC bar plus C. And these two terms, again distribution theorem, A plus B plus C into C bar plus C. Hence guys, for this term, the simplified expression is A plus B plus C. Okay, so in place of this you can write it as A plus B plus C. And one more, see this, AB plus BC bar plus AC bar. Now what you can write here, AB into C, ABC plus BC bar into C, 0, AC bar into C, 0. Hence, this term simplified expression is ABC only. Okay, so this is what here the minimized expression for this and for this. Now we are substituting this particular, these two, like in these two terms the simplified expression, and we will see what is the expression. Therefore the expression looks like this, that is AB whole bar, BC whole bar, AC whole bar into A plus B plus C plus ABC. Okay guys, again here we can simplify this term as well, that is A bar plus B bar, B bar plus C bar, A bar plus C bar, isn't it? Yes. And when you simplify this, what do you get? A bar into B bar, A bar B bar, A bar C bar, B bar, B bar C bar. Again this as it is, A bar plus C bar. Now again here it is like A bar B bar into A bar B bar. Similarly A bar into B bar, A bar B bar into C bar, A bar B bar C bar. Similarly here A bar C bar, A bar C bar, A bar B bar, B bar C bar, A bar B bar C bar plus B bar C bar. This one guys. So you can take this one, like 2 times it's appeared, leave it. And this 2 times appeared, this, you can remove this. And even this A bar B bar also appeared, then you can say A bar B bar plus A bar C bar plus B bar C bar. And even guys here this particular A bar B bar C bar, A bar B bar C bar, what you can consider, you can take in, like you take here only A bar B bar into 1 plus C bar, right? So this also gets vanished. And you take these two, you take B bar C bar common, then 1 plus A bar, right? It gets vanished. So here what I am telling is this highlighted term gives you the final term as A bar B bar plus A bar C bar plus B bar C bar. This is the term. Hence now again we are going to substitute in place of this one. Okay. So the simplified term is A bar B bar plus B bar C bar plus A bar C bar. Okay. And the rest of the terms as it is, A plus B plus C plus ABC. Now you see guys here, A bar B bar into A bar gets cancelled, 0. Again A bar B bar into B, 0. Therefore it is A bar B bar C plus, again the second term, here BC are there, BC gets cancelled, so that you get A B bar C bar. Similarly this one, AC terms are there, then it is A bar B C bar plus ABC. Finally, this is the term. And we want to know about the logic gate. What is the logic gate? They are not asking you the Boolean function. They are asking you the what is a logic gate. Okay. Now, here you see A bar and A bar. Then you can take the common A bar, B bar C plus BC bar. Again, A common, B bar C bar plus BC. So guys, you can rewrite it as A bar into B XOR C only, isn't it? Yes. Similarly, this can be written as B XOR C, because B bar C bar plus BC. And B XOR C can also be written as B XOR C whole bar. This one. Therefore, if you assume B XOR C as X, A bar X plus A X bar, that means A XOR X, A XOR B XOR C, that means the final expression is A XOR B XOR C. Finally, for this nested function, the simplified expression is A XOR B XOR C. Then what it is, guys? It is a 3-input XOR gate. If the function is this and the nested function is this, it represents the 3-input XOR gate. Okay. So this is what the nested function example. Okay. See you in the next video. Thanks for watching. This is Shivaram signing off. Jai Hind.